This video is about black holes, and it relates to Young and Freedman's University Physics, Chapter 12, Section 8, the last section of that chapter. So, black holes, you may have heard of black holes. The idea of a black hole is of something that is so dense that light even can't escape, and since light is the universal speed limit, nothing can move faster than light. Therefore, if light can't get out, nothing's getting out. And so there are black holes in the universe. This has been fairly well demonstrated, and so let's talk a little bit about them in relation to gravity. Okay, remember escape velocity from earlier in the chapter on gravitation, and I'm sure that your textbook, if you're using a different one, covers escape velocity as well. So the formula for escape velocity is basically that the escape velocity to leave orbit from a planet or a sun or whatever, you're going to have that velocity is going to equal the square root of twice the gravitational constant times the mass of the body you're trying to escape from, divided by the radius of the body you're trying to escape from at the point you're trying to escape from it. So, there you have it. Well, as early as the late 1700s, there was a guy named John Mitchell, he was a minister, who basically asked this question: at what mass would light not be able to escape a particular radius and mass to radius ratio? Since this law, or this escape velocity equation was known at the time, he simply set velocity equal to the speed of light and solved for the radius in relation to the mass. Now, as it turns out, this works, but it works by accident. It works because of this equation works, c equals the square root of so forth. It works because of a happy cancellation, that in reality this formula, which relates, it was derived in relation to the potential energy and the kinetic energy of a particular body. As it turns out, the kinetic and potential energy of light aren't exactly the same, as the formula for them isn't exactly the same as the formula for potential energy and kinetic energy of other material objects. But by happy cancellation, it works out that the formula works. So the formula works, but it's coincidence. So Rs equals 2gm divided by the speed of light squared. The S there in Rs stands for Schwarzschild. Schwarzschild was a Russian physicist who unfortunately died of illness prematurely in 1916. But Schwarzschild had basically predicted that there would be stars that were so massive that when they burned out, they would collapse in on themselves and, in fact, become infinitely dense as they collapsed. By the way, Einstein did not like this idea at the time, and Sir Eddington, who had done a lot of work with stars as well, thought it was a silly idea, and since they had the power, this idea was not smiled upon for some time. As it turned out, they died, and they were wrong. Anyway, Arthur Eddington was a good guy, I'm sure. But anyway, he helped prove relativity in its earliest stages. But anyway, this Schwarzschild radius is the radius at which, given a certain mass of a planet, it is destined, when it burns out, to become a black hole. So you can calculate this, that radius is going to equal twice the gravitational constant times the mass of the star. It's going to have to be a star. No planet is big enough to eventually become a black hole. It's going to be a very large star that's going to do that. 2gm divided by the speed of light square will tell you what the Schwarzschild radius is for a star that is destined to become a black hole when it burns out. Well, should we be worried? What about our sun? Of course, we're several billion years out, so I'm not worried about it myself, nor should my children be. But as it turns out, at least as far as the black hole, actually, we might be in better situation if our sun was destined to become a black hole. I think it's going to become a red giant, and when it burns out and becomes a red giant, I think basically the Earth will be enveloped. But anyway, hopefully by that time we'll have worked out, some kind of an artificial Death Star that we can all live on. Except we'll call it the Life Star. That's not important right now. So the when you figure out the escape velocity from our sun, the escape velocity turns out to be about 6.18 times 10 to the 5th meters per second. This is why the Starship Enterprise has such a hard time getting away from the sun. I don't know whether with a warp engine that should be the case, but anyway, that's the speed you would need to have to get out of the sun's pull if you were at its surface, which you'd immediately be destroyed. But again, not important. So the escape velocity from our sun is about 1/500th the speed of light. Phew! What that means is that our sun will never is not massive enough simply to eventually become a black hole. Basically, as it turns out, for a star to become a black hole when it burns out, it needs to be about 3 times as big as our sun, or about 3 solar masses. So we're safe as far as the sun becoming a black hole. The reason why I said we might be better off with it becoming a black hole is because things in orbit around a black hole continue in their orbits. Now, they don't get sucked into the black hole if they're orbiting, the star that becomes a black hole. And so we might be in better shape, if that were the case, than for our sun to become a red giant when it burns out. Okay, here's some other aspects to black holes. So we call the Schwarzschild, let's say a star has become a black hole and it has collapsed into a singularity, into an infinitely dense point. The event horizon is what we call the Schwarzschild radius. Basically, even though the mass of the black hole is no longer at the Schwarzschild radius, anything that passes the Schwarzschild radius, we say it's past the event horizon. And anything that passes that event horizon of the star that's become a black hole, it ain't getting out. Nothing gets out. No information, no light, nothing gets out. As it turns out, Stephen Hawking did demonstrate that black holes over time do, as it were, evaporate away. But that's a different part of physics. Or not. It's not in this lecture, let's say. So within that radius, the black hole becomes a singularity, a point of infinite density. And of course, as you approach that event horizon, time dilation takes place. So the chapter uses the example of if somebody were to sacrifice themselves for science and were to fly a spaceship toward the event horizon and radio things back. Basically, by the time the astronaut was approaching the event horizon, all the people listening for the radio waves would be dead because of the time dilation. Time will be stretched. Now, the person in the spaceship experiences it as normal time, but the people back home listening, they die out, before the person even gets to the event horizon. Tidal forces would rip apart anything approaching. Even when you get to the event horizon, my body would be stretched out to where basically my feet would be pulverized, pulled apart into atoms, a string of atoms, long before my head even gets there. But anyway, let's not do this. There are supermassive black holes. So how do we find these? Well, sometimes you can see what's called an accretion disk. Gases swirling into the black hole. So maybe there's a nearby star whose gases are being sucked into the black hole. Of course, as a body approaches the event horizon, it will emit X-rays as it heats up, and so we can tell sometimes that a black hole's there because of the X-rays being emitted. Stars rotating around nothing. So at the center of our galaxy, the Milky Way, there is a supermassive black hole at the center of our galaxy, a star that was once much larger than our particular sun is. We call this SGR-A. It's in the area of Sagittarius, but there's again, we can't see the black hole, but you can see the stars rotating around nothing, as it were. But the mass of that black hole at the center of the Milky Way is about 3.7 million times that of our sun's mass. Well, it's fun that Young and Freedman have thrown in something like this early into the book, 400 pages in or so. So that's nice. Threw us a little bone We didn't have to get to the end of the book to get to black holes. But, of course, a lot of general relativity that Einstein came up with is involved here, and that would have to wait for a later course. So there you have it, black holes. Oh, the Schwarzschild radius, before I finish, the Schwarzschild radius of this black hole at the center of our galaxy is about 1.1 times 10 to the 10 meter. So that is a big Schwarzschild radius.